So let's go ahead and get started. It's 3 o'clock. One thing I wanted to make an announcement about. Oh, really? Interesting. Even though, I mean, you only start recording at like 3 o'clock, right? I just turned my music off, so hopefully that doesn't happen. Okay, one announcement I wanted to make before we get started on sort of our objectives for today. I'm still getting emails, not that surprisingly, sort of last minute for the homework that's due later today. So I will be holding sort of like an office hours, not quite an open office hours because I have some students that scheduled this time with me, but I have students scheduled at 4 o'clock and 4:30 immediately after lecture. So if you had some questions about some problems, you can feel free to hop into the office hours during that time. But just so you know, that time is technically dedicated to those students who scheduled that time. So hopefully if their questions are in line with yours, then you can get your question answered. Yeah, so stop by the office hours if you might need some help. If they finish their questions early, then I'll be happy to open it up to any questions. But I sort of already have a list of students who wanted to get their question in. So we'll see what happens. Okay, so today's topic is going to be on co-flow heat exchangers. These are also known as parallel flow heat exchangers. And but before we get into that, I wanted to quickly review the energy balance for PFR because it's going to be useful in our example and sort of also understanding how we derive the energy balance for the heat exchanger. So let me zoom in here. Okay, so as you might recall, our energy balance for a PFR, we define as del Q minus the summation of Rj delta Hj divided by the summation of Ni Cpi. And I'm not going to go through the algebra of this. If you're interested in seeing how it's done, you can look in equation 8.3. But writing this same equation in terms of conversion, so in terms of conversion, we can then write it as dt dv is equal to del q minus r del h divided by, now this term on the bottom is going to look really ugly. However, when we get to the examples, and you'll realize that it's just a numerical calculation for a lot of these terms, and in some cases, when we can simplify this quite a bit. So this is going to be Na naught times the summation of theta I Cpi minus Xa over Va del Cp. Okay, and so this is simply just the energy balance in terms of conversion, and it's what we're going to be using when we get to our example today. So I wanted to just real quick look over that again. So as far as co-flow heat exchangers, so you probably already know from sort of previous explanations what a heat exchanger looks like. But there's a couple different types that we're going to be discussing in this class. There's a co-flow heat exchanger and counter-flow heat exchanger. Today we're going to be talking about the co-flow heat exchanger, and sort of the, as you're probably aware, that sort of general form of a heat exchanger is that, at least in the case of a PFR, when we get if we imagine our PFR pipe sort of being surrounded by a larger pipe, we can imagine that the inner pipe, which holds our process fluid, at least in the case of a exothermic reaction, would be sort of like a hot fluid. And then when it's surrounded by an outer pipe, which, in this case, you could call it a jacket, or it's just a pipe basically. But in this case, the pipe would be filled with a colder fluid that will cool the inner tube. And so probably a better way to show you what this looks like is to just show you a diagram, because I can't draw these very well. But basically, this is sort of what a co-flow heat exchanger would look like. The difference between a co-flow heat exchanger or parallel flow heat exchanger is just simply the direction of the flow in the utility fluid compared to the process fluid. So in this case, this inner tube here is the process fluid, and the outer tube is filled with our utility fluid. So in most cases, you're looking at like water, steam, oil. And what makes this a co-flow heat exchanger is specifically the fact that the process fluid and the utility fluid go in the same direction. So you can then imagine that a counterflow heat exchanger would be if the process fluid and the utility fluid go in opposite directions. But for today, we're just going to be discussing the co-flow heat exchanger. And so another sort of common depiction of these exchangers is detailed in your book. And so question was, is the VA term here in the equation the volumetric flow rate or a specific? It's sorry, it's the I believe the stoichiometric coefficient nu A. Okay. Actually, yeah, I believe that's correct. I have to double check it. I'll double check at the end of the class. I believe it's nu A, yeah. Okay. And so here's sort of like another common depiction of heat exchanger, at least in 2 dimensions. So in this case, our PFR pipe, our process fluid, is sort of this inner tube here, and we have a utility fluid that flows through the darker gray section and exits out the bottom. And when we write this in terms of an energy balance, we can look at sort of a cross section of this whole pipe setup with a jacket, similar to how we did with the energy balance when we derived that in chapter 7. And here we can see that in this case, this white section in the middle is still our process fluid, and the sort of gray areas on the outside would be where our utility fluid exists. And so we can write an expression here that will be that will define our energy balance for the utility. So here the energy balance for the heat exchanger is defined as the inlet to our volume minus the outlet, so the inlet energy to our volume from the utility fluid flowing in minus the outlet at V plus delta V, and then minus del Q delta V. Now, real quickly, I wanted to sort of specify, you might be wondering, like, why is this a negative term, minus del Q delta V? The reason that this term is negative is because when we defined our energy balance previously, we defined it with a positive del Q. And so that what that implies in the sort of derivation of our energy balance for the PFR is it implies that the it implies a given direction of heat flow. And so from the perspective of the PFR, our process fluid, the heat transfer is going from the utility to the process. So a positive del Q in this case means that heat is being transferred from the utility to the process. If heat is being transferred from the utility to the process, that means in the energy balance for our heat exchanger, we require a negative del Q to indicate that heat is flowing from the utility to the process. So everything has to be consistent because we're going to be using both equations in the example problem. And so in this case, from here, we can write we can write this as a first order differential equation. Are those capital or lowercase v's? Sorry, capital. These are so the inlet energies to the our volume, our control volume. These are all volumes. I think I capped all of them. Okay. So we can write this as a first order differential equation. dTu dV is equal to negative del Q over NU CPU. Because we have a first order differential equation here, we need to have an initial condition. And in this case, our initial condition is Tu of 0 is equal to the inlet utility temperature. And so this equation here is going to be important. And this is equation 815 in your text. So before we go into the example problem, just a quick reminder here, because it's going to show up in our MATLAB code. The material balance for a PFR in terms of conversion was introduced on Wednesday. So here it is one more time. dxa dV is equal to negative RA over NA naught. Okay. So with that out of the way, we can sort of go through an example here. So in our example, we have the reaction A goes to B is given as an organic liquid phase reaction that reacts in a PFR. A shell and tube PFR specifically. In this particular example, it's not specified what utility could be used, only that either H2O or air at 27 degrees C can be used to cool the system. So we're going to do a couple of things with this information. The first thing we're going to do is, well, not the first, but one of the things we're going to do is we're going to try to plot XA versus V, similar to what we've done before. And we're also going to plot T versus V. And we're going to have a bunch of assumptions. Well, not really assumptions, but just given information. So assume that K as a function of T is given as 0.3 times the exponential of negative 500 over T. Tau is equal to 30 seconds. CPA is equal to CPB, which is equal to 90 joules per mole Kelvin. I will point out that this particular specification was made, makes the calculation that we're about to do, or at least the energy balance calculation, quite a bit simpler. However, if they were not equal, then it's really just a matter of including a sum in your code, and I'll point that out when we get to it. Okay. Next up, we're given that the diameter of our tube is 10 centimeters. And we're given the specific heat of our potentially our air utility as 1,000 joules per kilogram degrees C, and our specific heat of our potential water utility as about four times that, so 4,000 joules per kilogram degrees C. We can also assume an elementary rate law. And I forgot one thing here. Kc is equal to, because we have a reversible reaction, we have to have our Kc term. So our Kc in this case is going to be equal to, so Kc as a function of t is equal to 2 times the exponential of 600 over t. You'll notice that a lot of these expressions here, so the k expression and the kc expression I'm giving you, I'm already giving you it in terms of t. Really, that's just to sort of simplify the code. If you were given, say, k at one temperature, then you would simply, make an adjustment to the a new k at a different temperature using the Arrhenius expressions that you're familiar with. And then last, I think this is going to be the last piece of information we need, is going to be del H is equal to negative 2,000 joules per mole. I think it's Kelvin, or joules per mole, those are units. Okay. So now the question is specified. So part A is going to be, if air is used as the cooling utility, I specify, by the way, I specify cooling because the del H is given as a negative value, which means that the reaction is exothermic. And so if the reaction is exothermic, then obviously our heat exchanger is not going to be heating the system, because then we'd potentially just get a runaway reactor and cause an explosion. That wouldn't be good. So if air is used as the cooling fluid, find the outlet temperature. Given that the mass flow rate of U, in this case of our gas, is equal to 0.5 kilograms per second. Okay, so before I switch to MATLAB, the first thing I'm going to do, and I think this is probably what most of you, I hopefully, are doing in your homework. I've noticed a couple students go straight into MATLAB and try to code everything into MATLAB. My personal preference to not only make sure that everything is that I can make sure all the calculations are correct, is to first do the write out the calculations on paper at least. Not integrate it, because I'm going to leave MATLAB to do the integrations, but at least write out the expressions that I'm going to be using, so that when I do code in MATLAB, I could just reference the equations and make sure everything is all kosher before I potentially have to debug things. So that's just a useful tip. So if you're one of those people who are prone to errors in MATLAB that aren't making sense, if you haven't already, try doing all the calculations and equations on paper first. So as we do it in MATLAB, because we generally recommend starting with your energy balances and sort of defining the equations backwards, I'm going to do the same thing on paper here. And so starting with the energy balance of our utility, we can define this simply as the expression dt dv is equal to negative del Q divided by NU CPU. Now, in this case, the utility balance as given here is expressed in terms of moles per second. Notice that here they give us a mass flow rate, and also notice that the units on our specific heat for the gas and the water are given in units of mass as well. And so what that means is that we can simply rewrite this expression to be negative del Q over mu CPU. And with that, all of our expressions should line up. Yes, you're right. It should be dTu, sorry. The temperature of the utility. Thank you. I might have made that mistake actually up here too. No, I wrote, yeah, so dTu. Thank you. And so the next thing, again, because we start with all of our material balance as energy balance, well, let's define the material balance for the PFR. In this case, it's going to be relatively simple. It's just going to be the expression that we have above, which is dxa dv is equal to R divided by NA naught. I think the expression I actually have above is R negative RA over NA naught, but we can express that as R NA naught as well. Now, before I go any further, because again, we're sort of going to be doing this in parallel with our MATLAB code, I do want to specify what we have and what we don't have expressed so far. So MU is given, CPU is given, so we're going to have those. DQ is not given directly. So I don't know why I put a check mark and said it wasn't given, but which means that we need to make sure that we describe that using the appropriate equation. So I'm going to write off to the side here what DQ is. DQ is equal to UA times TU minus T. Same thing in the material balance. Yes, that's that is a negative in front of the RA. Yeah. Okay. So same thing for the material balance. NA naught. Actually, I don't think, did I give NA naught in the problem? I should have. Does not look like I specified it. NA naught is 23 moles per second. Okay, so looking at our material balance, NA naught is specified, and R is not directly specified, but we know it's an elementary rate law, so we can define R as the expression K CA minus CB divided by KC, because it's a reversible reaction. And so moving on, we have the energy balance for the PFR. So there's no such thing as a dumb question. MUG is the mass flow rate of the gas utility. So it's just the, I made a conversion from moles, a molar flow rate to a mass flow rate. That's all that is. Okay, so no problem. The energy balance for the PFR is described by the expression dt dv is equal to del Q minus R del H divided by NA naught times a handful of summations. So that's going to be theta I CPI minus, in terms of conversion at least, is going to be XA over nu A del CP. Now, the nice thing about this is that, like I was saying earlier, we can simplify this because the given information here tells us that CPA and CPB are equivalent to each other, which means that my del CP down here is equal to 0, which crosses out this whole term here. Now, if that wasn't the case, you would simply plug that portion of the equation into your MATLAB, and these just becomes another constant essentially. But in our case, we're going to simplify the expression, and we can reduce this down to dt dv is equal to del q minus r del h divided by NA naught times the summation term here. And this can also be simplified quite a bit too. So theta is, the definition of theta is equal to Ni over Na naught. And in this case, we only have A coming in. Which also I think I forgot to specify here. So pure A. So pure A inlet. So pure A inlet means that if we were to solve for theta B is simply going to be 0 over Na naught. And which means that the only term that comes out of this summation is the A term. So we can get our final form down here to simply be Na naught times CPA. dt dv. Okay, so looking at sort of everything we have here, we have our expressions for the energy balance of the PFR. We have our expression for the material balance of the PFR. And we have our expression for the energy balance of the utility. And each of these is going to be used in sort of the MATLAB code I'm about to do. So give me 1 second while I set this up. So what I'm going to do is I'm going to try to share both the screen that you see right now along, like right next to my MATLAB code side by side, so you can see sort of how I go about writing the code in a little bit more depth. Okay, I'm going to switch screens here. Okay, can you see both the written words and the MATLAB up right now? Thumbs up in chat if you can. Is it readable? If it's not readable, then I'm just going to only focus on the MATLAB code. Okay, perfect. So like I said, we have our 3 expressions here, and as is typical, we want to ideally write our function sort of backwards. So we're going to start, I'll try to zoom in on the writing here, over here a little bit more. There, hopefully that works out a little bit better. And so we're going to want to write our code a little bit sort of backwards, starting with the material balances, energy balances that we have. And so we can start by saying dx dv is equal to r divided by Na naught. Our energy balance for the PFR is going to be dt dv dq minus r dh, r times dh, divided by, put these in parentheses, divided by na naught times CPA. Yep, that should be good. And then our last expression over here, dtu dv is equal to negative dq divided by mu times CPU. And I'm just double checking that this is correct because I don't want to have to debug this. And then finally, because our function is going to take an input of we're going to output the results from 3 different differentials. We have to specify that in our code here. So dy dv is equal to, in parentheses, dxa dv, dt dv, dtu dv. Okay, and so now we just sort of need to go through each of these and make sure that we have all the variables that we need to use in order to define each of these expressions. So let's start with the utility because it seems probably the shortest. So so like I said already, dq here needs to be defined as the expression that I have written off to the side over here. Mu is just going to be a given, and CPU is just given. So we'll start with that. Mu is given at 0.5, and this is in kilograms per second. CPA is given as 1,000 joules per kilogram degrees C. Mu, CPU, dq. And then we need to define the expression for dq. So dq is equal to u times a times tu minus t, which itself requires us to define u and define a. Each of these are going to be constant, so I'll put them up here. Oops. U and a. And so actually, in this case, u is not a constant, it's an equation. So u will be down here. U is equal to 1 over 1 divided by 1,000 plus, in this case, the if you look up at table 4.1, the HU value for gas is going to be 60, but I'm actually just going to put a variable there so we can modify that. Question, shouldn't NA be in the denominator of dt dv because the NA naught will cancel? This should be the correct form of the energy balance for the PFR. If you go to page, it's equation 8.3 on page 210. The algebra isn't shown on how they came to it, but they used the equations above it, which are 511 and 514. If you're interested, maybe stop by office hours and we can go through the algebra to show it, but that should be the correct equation. Okay, so we have our U defined, our A is simply going to be 4 divided by the diameter, I believe, yeah, which itself is an expression, so 4 divided by D, and then diameter is equal to 0.1, this is in meters, it was given as 10 centimeters. And so far, I think as far as dtu dv is concerned, we should have everything defined. So we just double check here, we define dq MU is defined, CPU is defined. Oh, CPU is not defined, not yet. So CPU, so CPU for the gas is, oh no, it is defined. I just mislabeled it. CPU. Question, so Ni should be Ni not for theta. Oh, you might be right. Let me double check. Yeah, it should be Ni not. So my mistake. Let me correct that. Yeah, Ni not. Okay. So A is defined, D is defined, U is defined, and DQ is defined. So we should be good. Next thing to do is define the variables in the other expression. So for our material balance, we need to define R. In this case, R is equal to K times CA minus CB divided by KC. And that requires us to define CA is equal to CA naught times 1 minus XA, and CA naught in this case is equal to NA naught times tau divided by V. Oh, stop.
Mic off, mic on.
Dog is growling at something outside. Sorry. Okay. We also need to define CB here. CB is going to be simply CA naught times XA in this case. That comes from equation 5.11, in case you're curious. So this is moles per meter cubed. So our CA is defined, our CB is defined. We do need to specify our NA naught, which is given in our tau, as well as our V, which I don't think I specified, but V was 1 meter cubed. That was part of given information. So V is NA cubed, or 1 meter cubed. NA naught is equal to 23. This is moles per second. And NA naught, CA, tau is given as 30 seconds. So I specified tau, specified V, specified NA naught, and then CA naught is specified as well as XA. And then the last thing I need to define is the K and KC terms. So K is equal to, it was given as 0.3 times the exponential of negative 500 divided by T. And KC is defined as a similar expression, 2 times the exponential of 600 divided by T. Okay, so looking, and again, just to double check, because as a general hint, or not hint, but sort of general tip, if you describe everything in terms of variables the way that we are, and then that allows you to backtrack to where you define the variables. So starting from our dxa dv equation, if I double click a given variable, so R in this case, it'll highlight it everywhere it appears in the code. So R is defined, and then I have to look at R. Well, I can see that K is defined, and this is just a set of constants because we're going to be inputting temperatures. CA is defined as here, which again is, will back out to nothing more than a set of constants, NA naught, tau, tau and V. And XA again is just a one of our inputs, because we're plotting XA versus T, versus V, and T versus V. XA and temperature for the reactor and the utility are going to be our inputs. And so everything here should be specified. And then the last equation to go through is the energy balance for the PFR, dT/dV. So dT/dV needs to be specified. In this case, what about HU? Oh, you're right, HU needs to be specified. HU for a gas from table 4 is 4.1, I believe, is going to be 60. And that's going to be 60 watts per meter squared Kelvin. This is from table 4.1, I believe. Thank you. And yeah, so last thing we need to specify are the expression for the energy balance. So here we already defined dq because it was used in the utility balance. And that means that UA are also defined by the various constants that need to be defined. Next is R, which is already defined from the material balance. So the only thing that we need to specify here is that DH, which is given as a constant. And DH was negative 2,000 joules per mole. So question, does XA need to be defined or do we input that? XA is going to be an input. Why are we defining V when it changes as the ODE happens? So that I'll actually I'll answer your question once I'm finished with this because it sort of goes to what the graph represents, but we'll discuss that. And then we need CPA. Do we need CPA? Yeah, well, we'll define CPA right now. So it hasn't appeared in the two balances I've done, the material balance and the energy balance for the utility. I don't think CPA has appeared yet, but I might be wrong. In any case, here we define DH and then NA naught is already defined. And like you said, we need to define CPA. So CPA was given as 90, I believe. 90, where is it? Yeah, 90 joules per mole Kelvin. Okay. So I believe this is everything. Okay. So our function should be fully defined now with all the constants. Now the only thing we need to do, I'm going to enlarge this, is we need to define the plot and the rest of the code and the inputs. So once we have this, we can say that XA is equal to Y of 1, T is equal to Y of 2, and TU, our three inputs are going to be Y1, Y2, and Y3 respectively. Here we can define Y as equal to our sort of three guesses. So this is basically going to be in the form of XA naught, T naught, and TU naught. So these are these define our sort of starting points. So here, this is going to be like our initial guess. We're just going to say the conversion is 0. Our temperature inlet, I think I specified the reactor temperature as 200. If I didn't specify it, I meant to. Looks like I did not. Yeah. Okay. So we're gonna assume T naught is 200 degrees C's. Could have swore I did, but it's in there somewhere probably. 200 degrees C, and because we're gonna do everything in Kelvin, I'm just gonna add 273 there. And then it's specified that either water or air at 27 degrees Celsius can be used as a utility. So our initial utility temperature is going to be 27 plus 273. Then we need to define our volume range. So V is equal to 0 to 1. The upper limit on that is specified by the fact that the volume was specified condition. So volume is equal to 1 meter cubed. So we're still going to be plotting over a range, but because we know that our volume is on the upper limit of 1, we're just going to stop at 1. We could, and I think we will extend that just to take a look at what the rest of the graph looks like. But for now, we'll do that. So we need to specify our ODE, which is going to be ODE 45 at func v range y naught. And oops, this should be v range. So v range is specified, y naught is specified. And then the last part here, I'm going to just copy and paste. This is just code that will actually plot it. So it's not super important as far as calculating the ODE is concerned. All of this code will be published with the lecture, so you'll get a chance to look at it. So hopefully, if I run it, I don't get any errors. And let me dock this here. So here we can see a couple things happening that we should expect. So in this first graph, we're looking at XA versus volume. And essentially, as we go further down the volume, remember that because we're in a PFR, our volume is related to the length of the PFR. So we could have plotted this in reference to the length of the PFR. We just did volume because that was what was given. We could have backed out a length out of that if we wanted to. And so what this graph would represent, if that was the case, is as we go further and further down the length of the PFR or down the volume of the PFR, we reach higher and higher conversions. And so that's what we would expect. As it's running through a longer and longer reactor, we'd expect that the conversion simply goes up and up. Similarly, for the temperature plot, here we have a plot of the utility temperature and the process temperature. Utility is in orange. And so recall that the del H value for this reaction was negative, which means it's an exothermic reaction. And so because it's exothermic, we need a cooling utility fluid. In this case, the orange line is, at least as of right now, it's using air. And so room temperature air at 27 degrees C. And so as you'd expect, the temperature of the utility goes up and will eventually match the process temperature. And the process temperature goes down at some point between the two, depending on the specific heats of the two fluids. So yeah, again, as if you can correlate the volume on the x-axis as the length of the PFR, which means that the further down the PFR you go, up until the maximum volume of our PFR of 1 meter cubed. 1 meter cubed as a volume corresponds to a given length based on the diameter of our tubing. And this basically is to say that at the given, down by the given length of the PFR, it corresponds to a given temperature of approximately 182 degrees for the outlet of the process. By contrast, the utility is just under that at about 180.4 degrees C. So question, when you define V is equal to 1 in the function, it overwrites the input from V span. Can you restate your question? I'm not sure what you're saying there. It shouldn't, if you're referring to the, by vspan, I think you mean vrange. If you're referring to that, the v inside the function only defines it helps to define the diameter and the what essentially comes out to be um, the system size. So if we're saying that we're going to work with a volume of 1 meter, this volume is really used to help define tau, which is used in the Ca naught concentration. So it's used to define the concentration, the initial concentration of A, essentially. Now, like somebody said, they were asking, let me see why are we defining V when it changes as the ODE happens? The reason is because this V that we're plotting on the x-axis is could correspond to the length down the PFR. So if our PFR is 1 meter cubed in volume, we want to know, given these conditions, if we were to go down 1 meter cubed, how what kind of conversion are we going to get? What kind of temperature outputs are we going to get? I just as easily could have plotted this down to, say, 5 meters. And I would also have to change the V in the here to be 5 meters as well. But if I plotted that, then this is what would happen if we got our system to be 5 meters in length, rather than just a meter long. Okay, so as far as what the question was asking, if air is used as the cooling fluid, find the outlet temperature given M is 0.5, so we found that to be about 182. And then the last thing that I will say about this is there was a part B to this question, which if you wanted to, you can sort of I'll post this code and you can play around with it since we're out of time here. But part B to this question was what water mass flow rate would you need in order to get the same outlet temperature if water was the utility? So you would have to change a couple values there, namely the CPU and the HU value to correspond with water. And let me switch back to just the whiteboard here so I can write out what the answer should be. So if water is used, then MU should be about 0.125 to get the same outlet temperature. And so I'll post the code and you can play around with that. Yeah, sorry, we ran a little bit over. Coding took a little bit longer than I thought it would, but I'll stick around for any questions. Just one more time to announce, I will have office hours for about an hour after class. So if you want to, feel free to hop in, ask some questions about the homework. Like I said, it is dedicated to the 2 students who did schedule that time, but if they finish early, then I'll open up to any questions. So, okay, I'm getting a lot of questions. A bunch of it is about the homework, but before I answered those, question was, what was the answer for A? The answer for A was about 182 was the outlet temperature in this example, 182 degrees C. Will the grade scope assignment be open tonight? Do you mean, are you referring to like turning in the homework? Is it not? Okay. Is it not available? Because it should be. Oh yeah. Okay, good. It should be available. Okay. Can you confirm if problem 4, point 4b has the correct answer? I could check that. Let me see if I have. I actually don't have it open on my or downloaded on my computer right now. I don't have the solutions downloaded, but I'll look over it. And I mean, if there's an issue with it, we'll probably send out an email. I don't think there is the last time I looked at it though. It should be fine. I'll just play some public domain music in the background since we're still recording. So question for homework 4.4b, are we supposed to assume that the maximum b for the yield equation is constant? I believe that should be the case. I don't have the question in front of me. Okay, there you go. There's your answer. It's not constant. So question is for 4.2, how do you make NA in terms of t, or would you make the function itself in terms of t? You can, I don't think you need to write it in terms of t. You should write NA in terms of, you can calculate NA actually directly because you're given a conversion and you can calculate NA naught. So in that case, NA is just equal to NA naught times 1 minus XA. Okay, I think we can probably end things here. So I can head over to my office hours. Feel free to hop in if you're interested in maybe asking some questions, or if you just wanted to listen to the questions that other people had. The office hour meeting ID for my office hours is listed on Canvas on the syllabus page.